Next up is a model that comes from magnetodynamics. This is again going to be continuous time 3D, but a little bit more complex. This one is going to take us to the limits of what we're able to do. This model is very famous. It's called the spinning disk model. It is due to Rikitake from the 1950s. Here's the setup. It's trying to model something about the magnetodynamics in the Earth's core, where you've got all this stuff sloshing around. So, simple model for this. You take two disks that are spinning. They each have currents running through them, and they each induce a magnetic field on the other disk. So you have it set up so it's like a coupled system, but instead of being coupled oscillators, they are coupled spinning magnetic disks kind of thing. Okay, well, here are your variables. You've got x and y, which represent the currents in the two disks. They are both spinning at some angular velocity z, and we have a pair of parameters. A is sort of a separation parameter between these two disks, and B is a resistive dissipation. Both of these parameters are going to be positive. All right, then, here is the Rikitake disk dynamo model. dx dt equals negative b times x plus y times z. dy dt equals minus ax minus by plus xz. And dz dt equals 1 minus xy. Polynomial system, it's kind of low degree, pretty close to being linear, but you've got a couple of nonlinear terms in there. Okay, what do? Let's find the equilibria. I'm going to set all these terms equal to 0. That last one, dz dt, tells us that x times y has to equal 1. Now I'm going to take the first two equations, dx dt, dy dt, set them to 0, and solve them for z. When I do that and set those terms equal to each other, what I get is bx over y, that's coming from dx dt equals 0, equals ax plus by all over x. Now I'm going to take this equation, multiply through by x and y, and what I'm going to get is bx squared equals axy plus by squared. I can use the fact that x times y equals 1 to substitute in here and get a polynomial that only depends on x. And what I'm going to get, moving everything over to the left-hand side, is that x to the fourth minus a over bx squared minus 1 equals 0. That is a quadratic polynomial in x squared. So I can use the quadratic formula, solve for x squared, and then take the square root of everything to solve for x. When I do so, what I'm going to get is that x is plus or minus square root of quantity a plus square root of a squared plus 4b all over 2b. All of that is under the radical. Now that is x. I can use the fact that x times y equals 1 to solve for y. It's just the reciprocal of that complicated expression. And then in the end, I can use one of my expressions for what z is in terms of x and y to compute that z is 1/2 times quantity a plus square root of a squared plus 4b. Now this looks complicated. It kind of is complicated, but what it means is that there are two and only two equilibria. And now we can do what we like to do best, which is linearize and classify these equilibria. So taking that right-hand side and computing the derivative of that, we are going to get what? The partials in x give us the first column, negative b, negative a plus z, and negative y. The second column is the partials in y. That gives us entries z, negative b, and then negative x. The third column is the partials with respect to z. Those are y, x, and 0. Now that's not bad until we have to substitute in those really crazy values for x, y, and z. At this point, I'm tired, you're tired, we're tired, please trust me, that the eigenvalues are as follows. Lambda 1 is negative 2b. That's negative because B has to be a positive parameter. The second and third eigenvalue are a complex conjugate pair, in fact, an imaginary conjugate pair, plus or minus I times the fourth root of quantity, A over B squared plus 4. That means that we've got something like a stable center. You've got one stable eigendirection, and then you've got this two-dimensional eigenspace where it's a center, maybe not. Hartman-Grobman kicks in and says, not so sure about that. So the thing to do here is going to be, look, let's simulate this and then just wrap this up. This won't be so bad. And so what do? Well, we pop this over into a simulator, a little visualizer thing. We just start letting a whole bunch of initial conditions go, and we see what the orbits are. Short term, well, it's not very descriptive. So if we integrate out for longer, we start to see a little bit of structure appear. We can see those two equilibria that seem to have center-like behavior in a plane about them, and everything else in that complementary direction seems to be stable, coming into it. But, oh my gosh, what is happening here? I mean, these aren't true centers. You seem to be spiraling out slightly away from them. It's not full of periodic orbits, and there are other things that are happening. You spiral out away from these equilibria a little bit, and then you sort of flip from one side to the next. That's kind of crazy. We're not yet able to really handle that kind of a situation. Yet, there's always Volume 4 where we talk about such chaotic dynamical systems. Now, let me point out that this model was originally intended to describe what is happening with the magnetohydrodynamics in the Earth, in particular, the somewhat sporadic flipping of the magnetic poles. There's some really intriguing behaviors that are buried inside of this system that may have some implications in terms of understanding the big picture. That is beyond what our goal is right now. Our goal is just to say, look, you can classify equilibria, but sometimes there's more to life than just that.